Tonight, Chapter 5, Network and Transport Layers. So we've talked about the application layer, we've talked about the data link layer. Now we're talking about the ones that are in between. And it's a good section to be looking at because this is, even though the other two are where you probably are closer to physically being able to touch or physically being able to interact with, these are the layers where you can code certain information. You can set up the properties, for example, for TCPIP and make your network work or make it not work relatively easily, but really more obscurely than simply a cable being unplugged or something of that nature. So an outline of Chapter 5. We'll start out, we'll talk about the transport and network layer protocols. There's a number of different protocols that operate at those layers. By far the most common are TCPIP, which are actually two separate protocols. We'll talk about those a little later when we get to that point. We'll talk specifically about the transport layer functions, what that layer is responsible for, what the various functions of that layer are for. We'll talk about the network layer, which is responsible for addressing and routing. So we'll talk about those functions as well. And then the chapter finishes up with a TCP/IP example. And I don't really expect you to know all the details of the example, but I do expect you to kind of be able to follow the flow. It should make sense when you see it flow. So that's really kind of what I want you to take away from that. So the transport and network layers lie between our application layer and our data link layer. And they're responsible for together, these two layers are responsible for moving messages from end to end in a network. So from the sending side to the receiving side, making sure that message on the receiving side is the same message that was actually sent. Both these layers work very closely together. That's why a lot of times when you hear people talk about TCP/IP, they tend to talk about that as a single protocol. The reality is they're two different protocols that each have their own unique functions, and we'll get to that here in a little bit. TCP/IP is by far the most common set of protocols that operate at these two layers because it's used on the internet. It's a very good, robust suite of protocols. It works very well with various other protocols that operate at the application layer, like HTTP, FTP, SMTP, so our web, our file transfer protocol, our email. TCP/IP works very well with those higher level protocols. It also works very well with our data link protocols, Ethernet, for example, or token ring. So most of the time we're on Ethernet, so we plug in our network card and our network cable into an Ethernet card. So our TCP/IP protocols work very well with those protocols above and below it. It's part of why it's so popular. So the transport layer itself, and when we're talking about the transport layer, we tend to talk about TCP, but not necessarily. There are other protocols that operate at that layer. The transport layer is responsible for end-to-end delivery of messages. It does that by creating virtual circuits when it's needed. You don't always create a virtual circuit at the TCP layer, but often you do. TCP does. This layer is also responsible for segmentation and reassembly. What happens when we send a file that's too big to go across as a single file? We have to break that file up into different segments. That's what the transport layer is responsible for, is breaking it up into smaller segments so that it can be sent across our network and then reassembled back on the receiving side. And then it interacts with the application layer. It also interacts with the network layer below it. Yes?
Does it have the limitation, like how much can it break down? Like, does it have any limitation, like there's a maximum size that it can break down and it won't break down after that?
Yeah, it actually comes down a maximum size?
Yeah.
I don't know about a maximum size.
I think our Tarleton email accounts doesn't allow us to add a file over 2 MB, right?
Oh yeah, that has nothing to do with TCP. That's an application layer restriction that the administrators have put on the email. So that's what that has to do with. What this does is it's restricted by ultimately your data link layer. Your data link layer only has so much room in it. So your data link layer has, and we'll get to that a little bit later, but your data link layer has a payload restriction. That plus any header information. So by default, that restricts the size of the layers above it as well. So all the layers have to work together. That's what I was just talking about a second ago, that TCPIP works very well with the application layer protocols as well as the data link layer protocol to make sure that it's not passing information that's too big for the data link layer to be able to take care of. Let's see. So yeah, the transport layer interacts not only with the application layer, but it's breaking up that message and putting a transport layer, usually TCP header information, and passing it down to the network layer, or it's doing the reverse of that. It's stripping the network layer off, address information off, and passing it on to the application layer, depending on the direction of the message. The network layer is right below the transport layer and just above the data link layer. So it's responsible for addressing and routing information. That's why it's very tightly intertwined with TCP, or the transport layer. The transport layer is responsible for that message getting from point A to point B. It doesn't care how that message gets there. It doesn't know how to get it from point A to point B. All it knows is that the message sent out was X, and then on the receiving end, it should be X. If it's something else, then there's an error. It needs to retransmit that message. The network layer is the layer that's responsible for that message going from this point to that point to that point, ultimately to the receiving end. That's what it's responsible for. It may pass bad data the whole way. It may get corrupted very early on in that in the transport from point A to point B, but it's only responsible for passing it on to the next node. The transport layer is responsible for it being intact. IP performs encapsulation on the sending end, and then performs decapsulation on the receiving end. So breaking that message apart and reassembling it. So this is what we're talking about. You see encapsulation and decapsulation occurring at every layer, because that's how it works. That's how we have interoperability between, say, a Linux box, a PC, Apple, etc. Is because we're able to encapsulate these different items and they all communicate in the same fashion. So at the application layer, if we're creating an email, we type up our email, and that email, as we hit send, gets appended with an SMTP header information to say this is who it's to, this is who it's from, this is the date, things like that. That gets passed down to the transport layer, who says, wait a minute, we work with the data link layer down here. I can't pass that much information. The data link layer can't handle that much information. We've got to break that message up into a couple of smaller pieces that are more manageable. But we also have to make sure that when we break those up, we can reassemble them on the receiving side. So we're going to add our own TCP header information that has things like the address, like sequence information, the order of the sequences as they're broken up, so that they can be reassembled over here in the proper order. Or if one's not received, it says, okay, send me this one that was, say, number 2. I didn't receive that one, so retransmit that one. The network layer does the same thing. It adds routing information at this point, the IP address. So it adds its own header information. Then it gets past the Ethernet data link layer. In this case, probably using Ethernet. That's normally what's used. We're going to add an Ethernet frame to it where it gets put on the wire. And then on the receiving end, we do the exact opposite of that. We start decapsulating those packets. So we strip the Ethernet frame off. We strip the IP header off. We strip the TCP header off. We get up here to our application that strips off the SMT message header, and it reveals the message to the receiver. So it sounds like a very complicated process, but that's the price that we pay to be able to have interoperability between the various types of systems that we have across the internet. Transport network layer protocols. Like I said, TCP by far is the most common transport and network layer protocols. Why? Because it's the language of the internet. So you see most networks use it, because if you want access to the internet on your local area network, you want to be able to have something that's compatible with what's going on. It's been around a long time. Our current incarnation of TCPIP, well, actually, the early versions of TCPIP have been around a long time. It was part of the original ARPANET, which was the forerunner to what we think of as the internet today. It's what's referred to as a protocol suite. a collection of protocols that all work together to be able to provide you services. So TCPIP don't operate by themselves. They work together with the other suite of protocols, such as ARP, which we'll talk about a little bit later, such as Ethernet, such as HTTP, etc. So that's a suite of protocols. As far as how good it is, it's reasonably efficient. We tack on all that header information, so that cuts down on how efficient it is, but that's the trade-off that we take in exchange for that interoperability. But for the most part, it's relatively efficient. It allows us to transmit large files with end-to-end delivery assurance, meaning that if we send it, assuming we're using TCP, it should get there. We shouldn't have any problems. We'll talk about why that's an issue here in just a little bit, like TCP versus something else. And it's compatible with a variety of data link layer protocols, mostly Ethernet. So TCP packet might look something like that. It links the application layer to the network layer, performs packetization, so it breaks them up into packets, and then reassembles on the receiving side. Numbers those packets with a sequence number, so that on that receiving side it knows the order of those sequences. You don't want to have a message that comes in all jumbled up. It won't make any sense. That's the responsibility of the TCP layer, or TCP protocol. And ensures reliable delivery of the packet. So you can see there's an awful lot of header information. I don't expect you to know what a TCP packet looks like. That I don't expect to get out of you. What I do expect is you to be able to look at one that's kind of noted like this and say, yeah, that makes sense. A source port, a destination port, sequence numbers, those terms for the most part make sense. So an acknowledgement number, which we'll talk about a little bit later when we get to that section, is basically what the receiving side would say, yes, I've received that packet. It'll send an ACK back. A sequence number, the order that they're in. The source port and the destination port, and we'll talk about those here in a little bit as well. That's how the server knows how to respond with what application. And some of the other ones are probably a little less important, except for obviously the user data. Any questions so far? IP, responsible for addressing and routing of packets. So IP is responsible, whereas the TCP is responsible for getting a packet from point A to point B intact, regardless of the actual path that it takes. IP is responsible for that path. There's a couple of different versions. There's the more common version right now, IP version 4, which is what most people think of. It's dotted decimal notation. It's when you see 192.168.0.1 is an example of an IP address. So it's 32 bits versus IP version 6, which was developed to try to address some of the shortcomings in IP version 4. Mostly that shortcoming being that we're running out of addresses. But there's some other reasons to go to IP version 6 as well. It does a better job. It's inherently designed with security in mind. TCP version 4, IP version 4 was before we put, however many billion people on the internet. It was really designed for a much smaller network or internet. So security was kind of a band-aid. It was an afterthought. TCP version or IP version 6 has security mechanisms built into it. It also has quality of service mechanisms built into it to allow preferential treatment of certain types of data. Let's see. This is what we were talking about just earlier, about the frame size, kind of related to what you were talking about. Ethernet has a maximum size of 1,492 bytes. So it doesn't care what part of that is header information and what part of that is user data. It doesn't care. It only accepts 1,492 bytes regardless. Anything else gets broken up into another frame. That's why it's important for TCP and IP to be able to work very closely with that lower level, or lower layer protocol, so that it knows the TCP header has 24 bytes, IP header also has 24 bytes, so the actual data that you can put is only 1,444 bytes per packet. that ought to look pretty similar to the TCP packet that we saw earlier. You're going to see very similar types of information in terms of obviously our user data, source address, destination address. They're located in different spots, but you see very similar types of notations. One of the things you should notice here is the source address and the destination address much smaller here versus down here in IP version 6, 128-bit versus 32-bit. Whereas the theoretical limitation of IP version 4 is around 4.5 billion addresses, practically it's quite a bit less than that because of reserved addresses and the way we've allocated addresses. That's why we're running out of them. With IP version 6, I don't remember what the number is, but it's some astronomically large number. We're not going to run out of IP version 6 addresses anytime soon. I think at this point I want to stop for just a second, and I want to go back and show you that video. I think that kind of helps to graphically show you some of what's going on here. Transport layer functions, linking the application layer, segmenting, and session management. TCP specifically, or the transport layer specifically. Linking that application layer. TCP may serve several application layer protocols. Can you think of any? Give me an example of 2 or 3 application layer protocols.
HTTP.
They're right there.
SMTP.
SMTP, email. FTP, file transfer protocol, a lot of times used to place web pages on a file server or on a web server. However, when you hit a particular server with an address, how does the server know how to respond with the right application? Let's say this server is operating a web server, an email server, and an FTP server. And you type in the address into an address bar somewhere. Well, it knows which application to respond to based on a port number that gets sent to it. Your web browser, for example, by default, even though you don't see it, by default appends every address that you send to a web server with the port number, port 80. That's letting the web server, or it's letting the server know that this is a request that's coming in on port 80. As a result, I need to respond with the web server in response to that request. If the port number came in on, say, 21, it would know to use the FTP server software to respond to that request. 25 for SMTP, etc. There's a set of standard port numbers, such as these, that are very common. You don't change those unless you have some kind of a security issue, because by default, like I said, a web browser automatically requests port 80. If, however, you wanted to have a hidden web server that was not easily found by people that were looking around, you could change the web server to look for requests on a different port. If that's the case, then you have to add a colon and whatever the new port number is at the end of the address to be able to access that web server. For the most part, you don't want to do that. Why? Because people, most of the time, you want to be found. So there are reasons, again, for security reasons. If you wanted a hidden website that you only wanted available to people that you gave the actual port number to, you could do that. But for the most part, you don't want to change from those standard ports. There's also non-standard port numbers, but requires configuration of TCP. Again, you have to go in and set the browser, or set the server up to be able to address those particular ports. So if you've got a client over here and they want to make a request, if you go back to those packets that we talked about, they had the source port and the destination port. Well, let's say you're opening up a web browser from this server. If, let's say, you don't have the IP address, or the domain name, all you've got is the IP address. You type in the IP address and hit enter, it automatically appends port 80 to that address. That request comes over here to the web server, and the web server says, I've got a request that's coming in, it's port 80, I need to respond with my web server in response to that request. So it's going to respond, but it responds back to this port. Responds to a different port. Why? Because this, you ever notice how you're able to open up multiple web browsers to the same web server? It's because you use different requests each time, different port numbers each time on your local end. That's what differentiates the different browsing sessions with the web server. Same thing happens with email or other types of applications that may be using other port numbers. As far as packetization and reassembly, let's say you're going to send an FTP file over to a receiver. So you open up your application layer, an FTP client, for example, where you're going to upload a file. TCP is responsible for breaking up that file into multiple parts, and it adds that TCP header information to each one of those parts. IP does the same thing, and it gets passed down to the data link layer, and then the reverse process occurs. The reassembly over here is what TCP is responsible for, is putting these back together in the proper order. Now TCP, like I talked about earlier, is responsible for those messages getting from point A to point B, right? TCP handles that, but you've got other protocols such as UDP, which operate at the transport layer, but don't really care about whether or not something actually gets to its destination. It wants it to. It's not trying to stop a message from getting to point B, but it's less concerned with it, I guess I could say. So TCP operates by being connection-oriented. It sets up a virtual circuit so that a message gets passed along the same path for the duration of that particular message. That's not to say that certain packets don't take a different route if you have a router that has some kind of an issue in the middle of a broadcast, or in the middle of a transmission, or you have some other type of issue that interrupts part of that transmission. You may have certain packets that will take a different route. But for the most part, it sets up that virtual circuit, and all your packets for that particular transmission take the same route. That's what HTTP uses, SMTP, FTP. That's how those particular application layer protocols operate. Connectionless routing is done by UDP. UDP is another protocol that operates at the transport layer. It's connectionless, though. What does that mean? That means it doesn't bother to set up a connection between the sender and the receiver. Usually it works with very small packets, in some cases just a single packet to be able to transmit information. So it's only appropriate when you're not particularly worried about a packet being dropped, because it's not setting up, it's not guaranteeing delivery from point A to point B. DNS requests, for example, are common, pings, and things like that. Related to this is quality of service routing, a special kind of connection-oriented routing that allows you to set priorities for certain types of transmissions, voice, for example, gaming, etc. So how do those virtual connections get set up? Well, it starts out by a TCP connection being set up. You send out a SYN packet to your destination. That SYN packet is designed to identify that there's a connection there, how much data can we send back and forth in each frame or each packet, the speed that we can transmit, because you've got to make sure that you can both take and send and receive at the same speed. So this whole process is going on right here in what's referred to as a handshake. At that point, depending on the type of routing that's being done, you're either doing a stop and wait, which is very slow. You send one packet, you get back an ACK or a NAC. You send one packet, you get back an ACK or a NAC. You wait each time for confirmation that that message really was received on the receiving side. More common is what's referred to as a sliding window. A sliding window allows you to do the same thing, but instead of waiting each time, you can send one, two. Depends on how much the speed control, the flow control between the client and the server, but that you've negotiated back up here. But you can send several pieces of data before you have to wait for an ACK or an ACK. If you get an ACK, that means it was received appropriately. Everything was okay. There's nothing bad about it. If you get a NAC, it says there's something wrong with that packet. I need you to resend it. So you go through that whole process back and forth, back and forth. Once you've completed, you close that connection. That circuit is now available for somebody else to use. So that's the approach that TCP takes. UDP doesn't worry about this. It just fires off the data. It's going to send it. Hopefully you receive it over there. Most of the time you do, but every now and then if you drop a particular packet, it's not a big deal for the uses that UDP is usually used for. So UDP, a protocol used for connectionless routing in TCPIP suite that uses no ACKs and no flow control. Usually they're very small packets because they don't require a lot of information to be sent or received. It's appropriate for pings, for example. Much smaller header, so it tends to be very efficient. It's used for things like DNS, domain name server, domain name service, DHCP, RIP, routing protocols, network management protocols. So protocols that tend to, application layer protocols, that tend to, if there's some kind of an issue, like a packet being dropped, tend to correct for it by rebroadcasting themselves anyway periodically, such as DHCP. If you don't get an IP configuration information as a client, you're going to send out a DHCP request again because you need it. But it also can be used in situations where you've got video, where the importance of having a reduced overhead, all that address information, etc., it's more important that you can crank out a lot of data quickly with less overhead because there's a lot of rich information in that video. With very rich information, you can lose a few bits and it doesn't cost you a lot, versus transferring a file, a Word file or something like that, one bit in the wrong place and that file's no good. With video, you can lose a little bit of quality of that video and it doesn't cost you. So it really depends on the specific application as to whether or not TCP is better versus UDP. Any questions? Okay. So quality of service, when we talk about quality of service, now we're starting to look at, probably in a little bit more detail, the differences between, say, TCP and UDP. We look at TCP versus UDP and we say, okay, well, must be different classes of packets that we're sending back and forth. Quality of service says, yeah, there sure is. In fact, it's more granular than that. There's email that's very unimportant for the most part, that if a packet happens to get there 5 seconds later, which is a lot of time in networking, that's not a big deal. That web pages are probably a little bit more important, that voice is probably a little bit more important than that, video is probably more important than that. We don't like when voice and video has a lot of delays to it. It gets very choppy and it's hard to continue a conversation. Quality of service allows us to prioritize those various packets so that we can make sure that the ones that are the most important to us get priority. They get shoveled to us or shoved to us as quickly as possible, at the expense of packets with less priority. And that's the idea behind quality of service. So things like video, things like gaming, where you've got real-time gaming applications that are going on, obviously voice and things like that. And I'll give you some of those examples down there. So the ability to support QoS, it's a suite of protocols that operate at the transport layer on top of IP. This is something that will be a little bit different as we get into IP version 6, with IP version 6 being able to help provide better quality of service than what we have with IP version 4. But you've got several different protocols that all work together to be able to, like I was saying earlier about security, provide kind of a band-aid approach to allow quality of service implementations across our existing infrastructure. Network layer functions. So we talked about earlier TCP quite a bit. Like I said, responsible for getting a message from point A to point B. The network layer is responsible for addressing and routing, so the IP addresses that we always talk about, IP version 4, IP version 6. Addressing each device on the path between source and destination must have an IP address. Not just an IP address, but a unique IP address. You can't have duplications. We're going to talk here in a little bit about the assignment of addresses, how they get assigned, whether they're static or dynamic, etc. and the translation between network layer addresses and other addresses. In networking, we traditionally talk about three different addresses: an application layer address, a network layer address, and then a hardware address, or logical and physical. And that's what facilitates our routing. Because we have different addresses, IP addresses, we're able to then take that and determine the best route for a packet to get from point A to point B. How do we do that? We look at the relationship between various IP addresses, and we can start to make decisions then. The fewest number of hops is one approach. We'll talk about that here in a little bit. The performance of a particular network segment. You know, obviously, if we could take fewer routes, in general, you might think that that's a quicker route, but not necessarily. If that route happens to be a very slow-performing network segment, it might actually behoove you to take more hops, but they're on a faster segments. So the types of addresses. We've got an application layer address, www.manhattan.edu. Something that most of us should be familiar with. They give you an example, like they refer to it as a URL. Technically, it's not. A URL actually, this is just a web address. A URL is actually the protocol, HTTP : / your actual domain name here, then the actual directory and the file name that you're actually pulling up. Even though you only type in this address here, you're actually pulling up an individual file, a home page, a default.aspx or HTML or whatever that file happens to be. It's a specific file that you're pulling up. That's going to be translated somehow, which we'll talk about here in a little bit, into an IP address. We remember words. It's easy for us to remember. But computers think in terms of numbers, specifically binary, so that actually is a representation of 32 bits. But this has to be translated into this. And then at the network, or excuse me, at the data link layer, we have a physical address of our actual network cards. So the process of translating this to this to this is a process referred to as resolution, address resolution. So how do those addresses get assigned? Well, at the application layer, for us as individuals, as users, you don't have to worry about that. Clients don't have addresses, application layer addresses assigned to them. Servers do, though. You want to have that www.tarleton.edu instead of having to remember the IP address. Some servers may have several application layer addresses. If a server happens to provide FTP services and mail services and those types of things, it's going to have multiple application layer addresses. The network address is done usually in one of two ways, either through dynamically being assigned by a DHCP server or statically assigned. Somebody decides that this is what the IP address is going to be. You manually type it in. It's certainly an approach. As networks grow in size, static assignments tend to become a little bit more difficult to manage because, like we were talking about earlier, you have to have unique addresses. If you've got duplications, one or both of the computers won't work. The data link layer address, you usually don't have a choice. Those, when you purchase the card, it comes with that address. Manufacturers make sure that they're unique addresses. Now, at this point, network cards have been around so long, there are some situations where you're able to adjust or change the network, or excuse me, the MAC address on a network card. But for the most part, you don't. For the most part, they're fixed. But again, you have run into that real problem that on the same segment, you can't have a duplication between your hardware addresses. Who assigns those internet addresses? You know, the www.tarleton.edu. ICANN does, or one of the groups that they work with. They basically go through the process of tying together your IP address and your domain name together so that that domain name represents that IP address. Both assigned at the same time and in groups. Let's see. Manages the assignment of both the IP and application layer namespaces. A lot of times you'll get the IP address through your ISP. If assuming you're going to go with the static IP, you'll get it assigned by your ISP, and then you would contact GoDaddy or one of the various representatives that works with ICANN to tie together that domain name with your IP address that you've been assigned. So then they give you an example down here. If you want to pull up, if you've got your computer up, pull up a browser and go to networksolutions.com/whois. Networks, yeah, there you go. Yeah, so now you've got to search all whois research. So type in a domain name. Any domain name you want. Type in indiana.edu. That'll give you back information about that particular domain, who it's registered to, what its IP address is, whether or not it's available. So you can see that it's registered, and its IP address that's associated with it is 129.79.78.192. So it starts out that 129.79 just like it is right there. So it's doing that through a process of resolution. It's resolving that domain name to that IP address. So kind of a neat little thing that you can do to kind of track down certain information about web servers, where they are. You can find information about who they're actually registered to. One of the things I'll do periodically is I'll get spam, and I'll go back and I'll do whois lookup to identify that a lot of times the domain names that you get for different spam email messages go back to the same place. And you can start to, if you identify the IP address, a lot of times you can block that IP address and block out a whole bunch of different domain names that are associated with one IP address. So play around with that. I think it's kind of interesting. Like I said earlier, IP addresses, IP version 4 is a 32-bit address. We break those up into dotted decimal notation, such as an IP address like that, 128.192.56.1. But the computer really only understands binary, so that's just a representation of a binary address. Now, like I said earlier, running out of IP version 4 addresses, there had to be a few ways to, there was the issue of trying to extend the life of IP version 4 and trying to figure out how we can get more addresses out of that. One of the ways to do that was to develop what they referred to as subnets, or classful addressing. And that's where we look at the part of an IP address, and part of it represents a network versus part of it represents a unique node on that particular network. As far as the different classes, for the most part, you deal with class A, B, and C. D and E are special cases that have certain very specific uses, but for the most part, you don't ever run into those. Most of the time, when you're dealing with your home network, on a personal network, you're usually in a class C network. What that means is that the first part of your address represents your network. Just those last 8 bits actually represent the different nodes on your network. That gives you 254 possible nodes that you could have on your local network. I say 254, there's 256 numbers, but 2 of them are reserved, so you only end up with 254. Class B, you end up with fewer possible networks, but more nodes per network. Versus a Class A, very few networks, but an awful lot. And I don't remember. That's works out to be like 16 million nodes per network, but not nearly as many networks. That's one way of looking at it. We'll look at subnets here in just a second. I think it's a little bit easier way of looking at it. IP version 6, instead of using those 4 bytes, it uses, which is a 32-bit address. Instead of using a 32-bit address, it uses a 64-bit address, which ends up with a really large number. So the idea is that because of poor IP address assignment very early on in the early days of of the internet, of squandering large sections of it by assigning large sections to individual groups that you couldn't then realistically take back because addresses had already been assigned, that we ran through an awful lot of IP addresses that we couldn't use anymore. So you see IP version 6 as a way to address that with a 16-byte address. Like I said, I don't know what that number is, but it's really, really huge. So chances of running out of an address using IP version 6 is very limited. Now, subnets is another way of looking at what we were just looking at a second ago with IP version 4. Groups computers on the same LAN with IP numbers using the same prefix, the first part of your IP address. So assign addresses that are 8-bit in length. In this particular case, everything that was on actually be, in this case, 8 bits in length for your individual nodes. So that's what it's talking about here. So this is a Class C network because we have 149.61.10 that are all denoted. When we see it noted like this, that means we're reserving this part for our network and this part for the nodes that we happen to have on our network. So that gives us between 0 and 255, 266 addresses. Like I said, 2 of those are reserved. A different subnet, 149.61.15, that's a different subnet. That means that these computers in here cannot talk to these computers over here without a router being involved because they're on different subnets. So when a computer on this particular subnet needs to talk to another computer on this subnet, it sends out what's called an ARP request, an ARP, that says, hey, I need to know what the IP address is associated with this MAC address. I need that information back. Well, if it's trying to contact one over here, that broadcast gets sent out, but it doesn't. It's never heard over here unless you're using a router to be able to transfer that message over to it. Assigned addresses could be more or less than 8 bits depending on how you want to subnet your network. You may not want to use all 254 addresses on a subnet. You may want to break it up to where you can have more networks with fewer nodes or fewer networks with more nodes per segment. It sort of depends on how you want to break up your network. Getting into the details of subnetting is way beyond this class, but just realize when you hear subnetting, it's a way to preserve addresses so that you've got more addresses available to extend the life of IP version 4. So they kind of go through an example here. This is what I was talking about earlier. These are all on the same subnet, Class C subnet. So 128.192.55, they're all on 5.5, and your gateway's on 5.5 on this side of the network address. So if you have these computers all over here can all talk to each other without any forwarding or any routing going on. Once it has to communicate with another node, say over here, it's got to send that request to the gateway, and at that point it doesn't know what's going on. All it does is it sends it to the gateway and it's done with the message. It doesn't have any say-so in how that message is routed over to the other gateway. That's the gateway's responsibility. The gateway has 2 network addresses. It has the internal one, which is on the same subnet as this one. It also has another network address that's the same one as the backbone. This gateway also has 2, one the same as the backbone, but then the different subnet over there, 128.192.56. So when that message gets sent here, the gateway says, oh, wait a minute, that message is not to any of these. I need to take care of that. I don't know where that goes, but I know that I can send it out here, and we'll let the routers up the chain of command make that decision. So it comes out here to, there should be probably a router up here. It comes up to this router. This router says, wait a minute, that's on this same subnet. So it doesn't know where it is over here, but it knows that this gateway knows where that address is. So it sends it to this gateway. This gateway now knows which particular client that's destined to. So it's a very hierarchical structure as far as how messages flow from one client to another when they're on different subnets. So how do we identify which one's a subnet versus which part of an IP address is the subnet versus which part is the node address? We have what's referred to as a subnet mask. So we might have an IP address that's 149.61.10.1, maybe a subnet of maybe an IP address of a particular client. We know that this first part is the network ID based on the subnet that's typed in, either manually or that we receive through DHCP. You're going to receive that information automatically if you're on a DHCP network. Can you pull up on your computer's a command prompt? I don't know if you can or not. Is there a run? Type in ipconfig. Can't do it. Okay. Never mind. I was going to show you some of the information that's automatically assigned via the DHCP server. Part of that information is not just your IP address, it's things like the address for your DNS server, things like your subnet mask, so that it knows which part represents the network ID versus which part represents the node itself, the host. So like I said, we can manually type in those addresses, and that's one way of doing it. There's problems with that. People make mistakes. You accidentally hit the wrong key, so you can end up with duplicate addresses and things like that. Certainly a problem. Hopefully through the use of dynamic addressing, you don't run into that problem nearly as often. Dynamic addressing allows a server, a DHCP server specifically, to be able to dynamically assign those addresses and make more efficient use of your IP address space. So let's say an ISP might have, say a small ISP may have several thousand subscribers. Do they need 1,000 or several thousand IP addresses at their disposal? Well, yes, if every single subscriber was on at exactly the same time. But the reality is they're not. So they could probably get by with fewer IP addresses, but by using a DHCP server, when a user logs in, they're assigned an IP address, their other information that they need, DNS servers, etc., subnet mask. And once they hang up, once they're done, that IP address goes back to the server, it's released back to the server then reassigns it to the next person that connects to that network. So it uses a server to supply IP addresses to computers whenever the computers connect to the network. A couple of common approaches. Bootstrap protocol, BootP, is not really used hardly anymore. It was kind of an early version of DHCP. Before that, you used what was referred to as a host file, which was literally a file that mapped IP addresses to domain names. And as the internet grew, that became very problematic. Why? Because you had to make a copy of that file and put it on every computer. As new computers got added to the network globally, that's kind of difficult to do. You can't ship disks all over the place. You can't email these things all over the place. It became very problematic to update those files. So you ended up with the advent of DHCP, which allowed a server to dynamically assign those without using a file. As far as these two compared to DHCP, they're similar as far as their basic operations, but they are a little bit different. A program residing on a client establishes a connection to a DHCP server or a BootP server. So there's two parts to DHCP. There's a client side that's built into your operating system on your desktop, and there's a server somewhere. If it's a small home network, that server is probably your router that you happen to use. A lot of times those will have a DHCP server built into them. If it's a large network, in a lot of cases, you'll have a computer that does that functionality. Computer, Windows Server 2008, gives you a lot more granularity. There are a lot more things you can do with it. For example, you can always assign the same IP address back to the same computer every time. If you wanted to, you can restrict the hours that a particular address is available. There's a lot of different things that you can do with a full-fledged DHCP server that something with a small router you might not be able to do. But there's a lot of different types of DHCP servers that are available. So when when a client first gets onto the network, it kind of has an identity crisis. It doesn't know who it is. It needs that information. So the first thing it does is it screams out and says, "Who am I? Give me my information. I need to know who I am." the server is going to look at its pool. It's going to look at its database of various IP addresses that it has available to it, the ones that it can assign. And then based on that, it's going to return that information back to the client. It's going to give that information back to the client. It's going to include that IP address, subnet mask, DNS server, gateway address, some of the important information that a client needs to be able to operate on the network. That's the process of DHCP. The process of address resolution, remember we have to translate those names that we did here just a little bit ago with Network Solutions. How does the computer actually go through that process of translating that name when we type in Microsoft.com or Indiana.edu? Goes through a process referred to as address resolution. We also have address resolution that happens at the data link layer as well. So there's a couple of different layers where you have address resolution occurring. So yes, question. All right. To be able to resolve the name between our application layer down to our IP layer, we use a DNS server. It's used to determine the IP address for a given URL, and it's provided through a group of name servers, domain name servers. Large organizations, they may run their own DNS servers. They're not the easiest thing to configure, so in a lot of cases, if you're a smaller organization, it doesn't make sense to do that. A lot of times you can use a service like Network Solutions to manage that process for you. It's much easier to do, and they handle all that for you. But that's what allows clients to be able to find you on the internet. When the domain name is registered, the IP address of the DNS server must be provided to register for the URLs in this domain. So you might have a domain name such as indiana.edu, but you've got subdomains as well. www, www.kelly, abc, etc. Those are all subdomains. They're all managed via that DNS server. So how does it act? What's the actual process? How does it actually work? Well, in a lot of cases, from your perspective, you've already typed in that address before, right? You usually visit the same sites over and over again. What happens on your local client is it develops what's referred to as DNS cache. It's basically a table or a database that's located on your local machine that once you've already queried a particular website, it stores that information in your DNS cache, and it makes it much easier to access the next time. Why? Because when you type in your address, it goes to your DNS cache and says, oh, we've already looked that IP address up. It just substitutes the IP address in, and it's a much quicker response to get back to that same web page that way. But if it happens to be a new website, or it's been quite a while since you visited that particular website, you type it in, and it's not in your table. Now it's got to access DNS, the domain name server. So it sends a DNS request packet to your local DNS server. That's the DNS information that you have configured on your local computer. Maybe you manually type that in. Maybe that was part of the information you got back from the DHCP server. But in either case, it's got to send that DNS request to that DNS server. So you send the URL to the local DNS server, and that local DNS server is going to respond by sending a DNS response packet back to the client of, yes, here's the IP address associated with that. Straightforward so far, assuming your DNS server has that information. If it doesn't, the process continues. That DNS server does a lookup to another DNS server somewhere up the chain of command, eventually getting back to a root DNS server on the internet. Usually it's not going to require that, but if you happen to have a host somewhere on the other side of the world that you've never accessed before, that happens to be part of attached to a network that you've never been near before, it may require going all the way back up to a root DNS server and then back and propagating back down. But you'll notice your delay time takes a little bit more when you access something like that. But it's very hierarchical in structure. It looks basically like a tree as it traverses up and back down. So they kind of give you an example here. If you're trying to access a server that's over here, if you've got it, it's just going to go straight to your LAN, from your LAN to the internet, to their LAN, and to the server, if you've already accessed that website and it's in your table. If not, it's going to send a request to the DNS server, and the DNS server is going to come back with an address and say this is the IP address of the computer you're trying to access, and then it's going to go to the LAN, the internet, the LAN, and the server. If your DNS server does not have it, though, now it's got to go from here to the LAN, to your DNS server, to the internet, to a root level DNS server. That then is going to return the information all the way back, and then you can make the direct link. So it can get complicated. Actually, it's not all that complicated. It just can kind of really extend that tree out quite a bit if you've not accessed that site before, and nobody else that's accessing your DNS server has accessed that site before. Does that make sense to everybody? Like I said, DNS can, especially the configuration of a DNS server, can get pretty complicated. I'm not worried about any of that in here. But conceptually, I want you to know what happens when you type in an address. How does it go through that process of resolving that name, Microsoft.com, to an IP address? And I think if you go back and you look at that particular graphic, it really helps to illustrate that pretty well. I want you to start to think about it. We have a similar issue at a lower layer in our networking model with the MAC address. When you try to talk to other nodes that are on your network, you've got to know what their IP address is when you go to talk to them. Well, a MAC address isn't routable versus a hardware layer address isn't routable versus IP is. So we have to use IP. So we have to have the ability to determine what the IP address is of the client that we're trying to send a message to. So we end up using address resolution protocol to be able to send a broadcast message that screams out. It's that identity crisis that I was talking about earlier. So it screams out and says, hey, I'm this MAC address. I'm looking for that MAC address, but I don't know what your IP address is. Send me that information back. And that's what ARP is. It's a broadcast to all the various nodes that are on your local segment to respond with your IP address. So it broadcasts that ARP message to all the nodes on the LAN asking which node has a specific IP address. Only the host with the IP address associated with that MAC address responds. Your local computer now will store that MAC address in a table again. So we have a lot of tables that are being saved on your local client. So that in the future we don't have to do that. Whenever possible, we don't want to broadcast messages. Why? Ties up bandwidth. The more we broadcast, the more likely we are to have collisions, and we want to avoid those. So we try not to broadcast messages. So if we can learn what that MAC address is tied to an IP address, we're going to keep that information for future use. And then at that point we can send the message to its destination. A MAC address might look something like that. Yes, that is a series of numbers. It's in hexadecimal. So again, computers talk in binary, but it's easier to look at that number in hexadecimal than it is to look at all the ones and zeros that it actually represents. Okay, so routing. The IP layer, or the network layer, I should say the network layer IP, the way it works, allows us to route messages from various nodes across the internet to be able to transport a message from point A to point B. So whereas transport is responsible that message gets there intact, IP is what's actually responsible for moving it along from from step to step or hop to hop. It does that by looking at routing tables, and these routing tables are created in a number of different ways, and we'll talk about some of these routing protocols and things like that here in a little bit. But it generates routing tables. Every node generates its own routing tables. Routing tables used to make routing decisions. Where's the next best hop? You know, if I get a message, where do I want to send that message to? It shows which path to send packets on to reach a given destination, and it's kept by computers making routing decisions. That can be a standalone router. It can be a computer performing the functions of a router. So routers are special purpose devices used to handle routing decisions on the internet, and they maintain those routing tables. So if you're trying to get a message from A to G, obviously you can just go A, B, C, G. be one route. But what happens if you have a route that goes down, a path that goes down? Well, there's alternative ways to get there. And that's part of what the routing table is designed for, is keeping track of the various ways to get to other routers on the network. In general, there's two types of routing. There are two general categories of routing. There's centralized versus decentralized. Centralized is fine for small networks. Why? Because it's pretty easy to manage. But the reality is that the internet, as big as it is, there's no way you can possibly account for every single route that exists on the internet. The table would be just monstrous. So there's no way to do that. So the internet uses what's referred to as decentralized routing, where the decisions made by each node are independent of the other ones. So in other words, each router, each routing device is making its own decisions, keeping track of its own routing table. To be able to determine what the most efficient route is, it's got to periodically exchange information with what it knows with the various routers that are nearby it, so that it knows, as it receives something, where's the best place for me to forward this to. It's kind of got to know what's going on around it to be able to do that. Static routing, types of decentralized routing, static routing versus dynamic routing. Static routing is fixed. You might have certain addresses that are priorities, that you want most of your messages to take a specific route. For the most part, we tend to try to avoid that because it's very difficult to, as routes change, as routes go up, come online, or routes go down. For example, somebody cuts a line or something like that. Dynamic routing doesn't adjust to that very well. You have to manually go in, make adjustments to the routing table, and that can be problematic. So as a result, dynamic routing tends to be much more popular, where the routing devices themselves go out and communicate with other routers in its area in order to be able to exchange that information as links come up versus as links go down. So how does it make a decision on which route is the best route? Well, there's a couple of different general categories of routing algorithms, and then within those algorithms, there's some specific routing protocols that we'll talk about. The two general routing algorithms are distance vector versus link state. Distance vector is the simplest. It just basically says whatever's the closest is going to be the quickest. And all else being equal, that's true. But rarely in life is all else equal. So there are some shortcomings to it. So again, A to G, the shortest route is probably going to be A, B, C, D. It's the fewest number of hops. 1 hop, 2 hop, 3 hops. It's a short number of hops. So that's what the distance vector approach would take. RIP is an example of a distance vector routing protocol. It's one of the very early routing protocols, and it's a decent approach for a rather simple network. But as the network gets bigger and bigger, and you start to have significant differences in performance between different segments on a network, it doesn't necessarily make sense. So if you have a break in the line, or this connection here gets really, really busy, it may be quicker to send another message the longest way, the most number of hops, just because this line happens to be really busy. That's where link state comes in. It's a more robust algorithm that attempts to identify not only the number of hops, but also how busy is the network, what's the bandwidth of a particular segment, things like that, to be able to determine what's the best route to be able to get this in the shortest amount of time, rather than just the fewest hops. So some question? So some specific routing protocols. Actually, I should go back for just a second. We're talking about routers here, right? There's 3 different classes of routers, if you will, general classes of routers. There's interior routers that operate internally to your network. There's exterior routers that are outside of your network. And then there's gateway routers that sit right between your network and the exterior world. In a small network, you really only have that gateway router. It performs not only routing functions at that level, but also your interior routing. But as the network grows, you end up with more and more interior routing. The reason I bring that up is some of the routing protocols operate at different, depending on whether it's an interior router, an exterior router, or a gateway router. Okay, so routing protocols are used to exchange information among nodes for building and maintaining routing tables. It's got to exchange that information with the routers that are near it to know what's the best path. So again, we go back to our thing over here, our diagram. Say this is these are routers rather than actual nodes. This router doesn't operate in isolation. It kind of wants to know what's going on over here, what's going on over here, so that it can determine the state of this link, the state of this link. It wants to talk to them and share routing table information. It can't share them with all of them, but it can share it with some of the ones that are closest to it in order to be able to help it make the best decision for forwarding packets. Autonomous system, a network operated by an organization such as Indiana.edu. Protocols classified based on autonomous systems. Types of routing protocols. Interior routing protocols, the ones that operate internally to your network. RIP, like I said, was a very early type of routing protocol. And for smaller networks, there's certainly no problem with that. Most of the time, your interior routers are going to be small networks, so it's not usually going to be a big deal if you're using RIP. You just wouldn't want to use it on the internet. A couple of other routing protocols: OSPF, Open Shortest Path First, EIGRP, ICMP. These all operate within a network inside of that autonomous system. Exterior routing protocols, such as BGP, border routing protocols, operate between networks. So that's what allows you to route stuff between your local network and exterior networks, is through a border router. So RIP, and more specifically, a dynamic distance vector interior routing protocol. So all it's looking at is the number of hops. How many hops does it take for me to send this packet from the source to its destination? Whatever the fewest number of hops is how I'm going to send that, regardless of how busy the network happens to be on that path. So once popular on the internet, now used in simple networks. The internet just grew too big for it. Operations manager builds a routing table using, not by suing, but by using RIP. Routing tables broadcast periodically every few minutes by all nodes. So remember, they have to communicate with each other, right? What did we talk about just a little bit ago about broadcast messages? Routing tables broadcast periodically. It ties up bandwidth. It increases the chances of collision. It's taking away bandwidth from other information that we as consumers want. We need our equipment to be able to route our messages, but at the same time, that takes away from us seeing our video or sending that email or receiving that file. So we want to reduce the overhead as much as possible. That's why IRP is not necessarily the best choice, especially in larger networks. When a new node is added, RIP counts the number of hops between computers and updates the routing tables. Open Shortest Path First, a dynamic link state interior routing protocol, became more popular on the internet. More reliable paths, incorporates traffic and error rate measures, so now it's starting to look at not just the number of hops, but it's starting to address the performance of the links between those different routers. It's less burdensome on the network. Only the updates are sent, so it's not sending an entire routing table. Only the parts of the table that actually change are being sent. So now the information that's being shared is less in size, so it's not tying up as much bandwidth. So it's preferable over RIP. Other interior routing protocols: EIGRP, a dynamic link state protocol, developed by Cisco. Very similar. A lot of this stuff is very similar as far as the different routing protocols at this point. Keeps routing tables for its neighbors and uses this information in its routing decisions as well. ICMP, a very basic routing protocol, error reporting protocol that helps to report routing errors. So when there's a problem, it reports back and says, there's a problem with this particular link, this particular path. We need to adjust our tables accordingly. And exterior routing protocols for border gateway protocol used to exchange routing information between autonomous systems. So our LAN and somebody else's LAN, the internet, for example. We have to be able to route packets from us at Tarleton to Microsoft or to whoever, somebody that's outside of our sphere, outside of our network. So we have to have the ability to route those packets across different networks, and that's where a protocol like Border Gateway Protocol comes from. Based on dynamic distance vector algorithm, much more complex than interior routing protocols. Why? Once you leave our border, our border router, the number of routers goes way up. We can't talk to every router on the planet. We'd spend all our time sharing routing information. So it becomes much more complex about how we're going to go about talking to different routers. So we try to identify the routers that are closest to us, the ones that we're going to interact with the most, and share information with them so that we can kind of anticipate the most efficient way out to a certain distance. And then we kind of rely on the routers that are out there to make the smartest decisions for our message to continue on its path to wherever its destination happens to be. Provide routing information only to selected routes. Privacy is a concern. As you send those packets out, now you're kind of trusting the routers to make the right decision, that it doesn't send your information to routers that are not necessarily trusted. Why? Because a lot of information is passed in plain text. If people are sitting there listening in, other than trusted ISPs and stuff of that, groups of that nature, they might be listening in to some of the things that are going on. If you end up with too many routes, you can't maintain your tables of every single route. That's the internet. You just can't. That's why you have to have a protocol such as this that can kind of address that and say, we're not going to look at every single route. We're going to identify only the most important ones to this particular router. So internet routing using Border Gateway Protocol, Open Shortest Path First, and RIP kind of gives you an example of some of the protocols that might be operating internally. So you have an interior router that may be using Open Shortest Path First. Over here you may be using RIP. Over here you're using Open Shortest Path First. But between different networks now, we're going to use BGP. It's an exterior routing protocol. Any questions? I want to show you a video before we actually do if that video comes up, before we actually do the quiz, because I think it helps to kind of illustrate how packets kind of traverse the internet. Multicasting is kind of a unique way of getting data pushed out across the network. For the most part, we've talked about unicasts. We log into a network and we want to download an email message, for example. That's a unicast. We send a message to our email server. Our email server responds to us. We're not asking multiple servers to give us our email message. Those email messages aren't being sent back to a bunch of different clients. It's just us and just the email server. So that's a unicast example. There are occasions, though, where we want to be able to broadcast or multicast a particular message. So broadcast, for example, we talked about earlier with respect to ARP requests. Ethernet, we don't know what a particular IP address is of a client that's on our network. So we send out an ARP request, which sends out a broadcast message to all the computers on our local segment to say, respond to me if you're this particular IP address. Multicast is a segment of that. It allows us to identify specific computers on our segment and broadcast a message to just that selected group of computers. So we may have, for example, a podcast that we want to send to just these first two rows of computers. It's common, especially here on campus, one of the ways that they re-ghost machines is through multicast. They can identify specific machines at night and send out a multicast message to be able to re-ghost those or re-image those machines remotely. So it's a way to send a message to a group of selected computers. Not all computers, just a selected group. IGMP provides a way for a computer to report its multicast group membership to adjacent routers. We have to have a way of identifying that subset of group of computers, and IGMP is a way to do that. Basically, those reserved IP addresses, the classes of IP addresses that we were talking about that I mentioned earlier, that's where this comes in. It's a special IP address assigned to identify the group. Routing node sets MAC address to a matching MAC address. When multicast session ends, IGMP sends a message to the organizing computer or router to remove the multicast group so that it can then go back and continue to receive messages the way it's supposed to be able to send messages. Let's see, sending messages using TCPIP. Required network layer addressing information. You've got to have, as a client, you've got to have your client address information. You've got to have a subnet mask. You've got to have a DNS server identified, and you've got to have an IP address of your gateway. Those are the 4 critical pieces of information that you have to have on your client. If you don't have those, you're going to run into problems. If you don't have a DNS server identified, can you still connect to the internet? Yes, you can. But you better know the IP addresses of all the servers you're trying to access. So you can type in your IP address and still access computers. Obviously, it's a lot easier to type in Microsoft.com than it is their IP address. So for the most part, DNS servers are required. If you don't have the IP address of your router or your gateway listed, there's no way for your computer to access an address outside of your local area network. It doesn't know where to send requests that it doesn't know are locally on your network segment already. So those are required of all the clients that are on your network. Address information obtained from configuration file or by DHCP, which we already talked about. And if you were to manually go in and look at some of your properties for your network card, you might see something like that. If you come over here, you see that it's assigned by DHCP, so that means you don't have to worry about typing it in. This particular client's already been set up to receive its information via the DHCP server. What information did it receive? It received that IP address. It received that subnet mask, which says that this is the part of the network ID, and that 100 is the specific client that happens to be on that network. It means you can't have any other clients with that same IP address. If you had another subnet, and this was a 2, that could be at 100, but that's a different subnet. And then you got that default gateway that's identified there. So if you send out a message and it doesn't know where to send it, it's going to send it to the gateway, and it's going to let the gateway do what it needs to do to identify where that message needs to go next. If you click on details, you end up getting additional information. That MAC address, the hardware address of the network card, same IP address, same subnet, same default gateway. The IP address of the DHCP server, so who's sending this information to it, happens to be the same as the default gateway. It doesn't have to be. A small network is going to be that way. Usually it's the same device. On a larger network, you may have a dedicated DHCP server, which is different than the gateway. It tells you when the lease, your DHCP lease, was obtained and when it expires. So at that time, if this computer is still connected to that network, that lease will expire. It will lose connectivity to the network. Usually that doesn't happen. Usually it will release your IP, release the DHCP address for another period of time. And then in this case, it happens to have 3 DNS servers associated with it. That's a good thing. Why? Because DNS servers do periodically go down. And if that's the case, you won't, for the period that that DNS server's down, if you go to a unique address, you won't be able to get that particular site up until the DHCP server comes up. In a lot of cases, what they're doing right here is a very good thing. You've got 2 DNS servers that don't appear to be related to each other. These 2 right here, 24.12.70.15 and .17, they're probably run by the same organization. Well, if they are, or the connectivity to them just above them happens to go down, you've lost access to not one, but both DNS servers potentially. So it's always kind of a nice idea to have another DNS server somewhere else. You can actually Google Google free or open DNS servers, and there's certain open DNS servers that you have access to. And it's not a bad idea to add those sometimes to your configuration, just in case the DNS server that you are using goes down. And then they kind of go through their DNS or their TCPIP network example, and they give you a graphical layout of all the various clients and how they're configured, and that they're on different subnets. And if you look through the next few examples, they talk about if you have a known address on the same subnet, of how that message gets processed. So this particular client requests a web page from this server, which is on its same subnet. The client already knows the server's IP and Ethernet address. So let's say over here, is it that one specifically? No, it's 130. Where do you see that IP address? .1.1.com. It's this one right here. So this client right here requests a web page from this particular web server. So it's on the same subnet. It already knows the IP address of it. It already knows the MAC address of it. That's a best case scenario. That's going to be the fastest time you're ever going to get a web page back. So operations performed by the client. It prepares that HTTP packet to send it to TCP. So you type in that web address right there. It places the HTTP packet into a TCP packet and sent to the IP layer. The TCP packet into an IP packet adds a destination IP address. Because it already knows the IP address, it doesn't have to look it up. So it's going to go ahead and add that to the address information of the IP packet. You're going to use the subnet mask at that point to see that the destination is on the same subnet as itself. So it's not going to send it to the border router because it knows it's on the same subnet. Add the server's Ethernet address into its destination address and send the frame to the web server. Why? Because you already knew what the MAC address, which MAC address was associated with that particular IP address. In response, on the server end, it's going to receive that Ethernet frame, and it's going to go back up our networking model. So now we're going to process that incoming frame up the various layers, data link, network, transport, application, until the HTTP request emerges to the server. The server says, this is on port 80. I need to respond with a web server to that request. So it processes that HTTP request and sends it back with an HTTP response, the particular web page that we requested. So we process that outgoing HTTP response the exact same way, but in reverse. And it goes back across an Ethernet frame to the client. On the client side, we receive that Ethernet frame back up the network model until we end up seeing it in our browser. If we know the address, but it happens to be on a different subnet, it complicates it slightly. Not too much, but just slightly. So the difference is, use the subnet mask to determine that the destination is not on the same subnet mask. What does that mean? That means now, instead of sending an ARP request or anything like that, to identify the local computer, the local node that it happens to be, we're not going to bother with that. We're going to send it to our router or our gateway. So we send outgoing frames to the local subnet's gateway. Local gateway operations it to receive that frame and remove the Ethernet header and determine the next node via the routing table. So where do I need to send that particular packet? That's what this process is going through. Now we create a new frame. The gateway creates a new frame and sends it to the destination gateway. So let's go back here for just a second. So I don't know where it's going. It's going somewhere over here. But so it repackages it and sends it on to its destination gateway because it knows now this subnet is on this same subnet. Interior subnets are different. This one is the same. Make a new frame and send it to the destination gateway. The destination gateway removes the header, determines that the destination is inside of its current IP address range, or address range. It places the IP packet in a new Ethernet frame and sends it to its final destination. At that point, everything else is exactly the same on the receiving end. It gets sent out to the specific client inside that subnet. Now, when you don't know the address, it's a completely unknown address, you have to determine the destination IP. You send a UDP packet to the local DNS server because you don't know it. You've never seen www.microsoft.com. So as a result, you've got to first do a query for that, find out what is the IP address associated with that particular DNS name. So you ask the DNS server to give you that information. The local DNS server knows the destination host IP address. That's great. It's going to send you back a DNS response with the corresponding IP address. If not, then it's going to send that DNS server is going to send a UDP packet to the next highest DNS server, back up the chain of command until it ultimately gets a response and can return back with the appropriate IP address. And at that point, then it continues through, just like step 2. TCP connections. Before any data packet is sent, a connection is established. Remember, we talked about that using TCP versus UDP. It does that by using a SYN packet, and then it closes that connection with a FIN packet. Handling of HTTP packets. Older versions of HTTP, for each connection, for each HTTP request was a separate TCP connection. What was the problem with that? We're wasting a lot of time here establishing connections and breaking those connections down. With newer versions, because we tend to spend more time, once we're on a website, we tend to stay on that website. We go from page to page to page. Rarely do we just open up a web page and then close it. We usually browse around a little bit on that particular web page. So newer versions, the latest version of HTTP, opens up that connection and keeps that connection open, so you're not having to constantly open that connection, break it down, open that connection, break it down. So it tends to be a little bit more efficient. We're just about done. So then they talk about the TCPIP and layers, host computers, gateway routers, and all the various steps along the way. Host computers, the packets move through all the different layers. So those OSI model would be 7 layers. With our model, we've got 5 layers: the physical layer, data link layer, network layer, transport layer, and application layer. So when we're on a host computer, those packets are going to move through all those different layers as we send something out. As we receive them back, they go back up those different layers to our application layer. Gateway routers, packets move from the physical layer to the data link layer, and that layer through the network layer. So a router doesn't process all that information. It doesn't go all the way up to the application layer in most circumstances, most cases. There's some situations where it might, but for the most part, it's just going to open up part of your packet to inspect it, to identify the address, because it needs to know where to forward it to the next one. So that gateways and routers don't go through all the different layers. At each step along the way, Ethernet packets are removed and a new one's created for the next node. Why? Because when it opens it up, it needs to know where it's going. It's then got to repackage it. Well, it's already discarded that Ethernet frame, Ethernet header information. So now it creates a new Ethernet frame around that information and sends it to the next node. Same thing with IP, and above packets never change in transit, created by the original sender and destroyed by the final receiver. So while the Ethernet will frame from node to Ethernet address information will change from node to node, your IP information is not going to change. Your application layer address is not going to change from node to node. It wouldn't make any sense. You type in Microsoft.com, if it changed at some point, you're going to end up with Google, and that just wouldn't make any sense. So that information stays the same. And it kind of walks you through that whole process. Implications for management. It says most organizations moving towards single standard based on TCPIP. I don't agree with that statement. They're not moving, they're there. I mean, virtually every organization is going to use TCPIP because of the need to be able to access the internet. There are probably some rare instances where somebody would not, for security reasons, for example. You want to be on a different protocol. But for the most part, the advantages that you get by using the same protocol outweigh most of the concerns, and so we take other steps to be able to secure our systems. Certainly, decreased cost of training networking staff. because it's by far the most widely used suite of protocols, TCPIP and Ethernet, etc., lots and lots and lots of people are familiar with it. That means the more people are familiar with it, the lower the costs are for personnel that understand that type of technology. So it's cheaper to be able to run your shop on standard protocols. Telephone companies with non-TCPIP networks are also moving towards TCPIP. I would say that is probably true, but to a large degree, a lot of that has also occurred as well. A lot of your traditional telephone lines have been converted over, and they're becoming digital networks, and they're being broadcast across packet switch networks rather than circuit switch networks. It's just more efficient to be able to do so. Certainly has significant financial implications for telephone companies. Why? Because they've been in the business for years of transmitting not only voice calls, but also data. Well, if they can reduce their separate networks down into a single network, they don't have to have nearly the investment in two different types of technologies. They can converge those types of technologies, and as a result end up saving quite a bit of money that way. Has a similar effect for equipment manufacturers. They're not having to support different technologies for different infrastructures, for voice infrastructures as well as data infrastructures. So that is that chapter. That's a complicated chapter.